Okay, so here's where we were last time. We were talking about how to do second derivatives with the chain rule. And so just a quick reminder of what we did last time. Z is a function of x and y, and r and theta are the usual polar coordinates, and that gives us this diagram. We start off by taking the partial with respect to r. So there's z with respect to r. We have two paths, and thus two terms. Right? Going really quickly because we did this last time. Then these terms simplify a little bit because you got to keep in mind that r and theta are the usual polar coordinates. And so the partial of x with respect to r, partial of y with respect to r. I mean, x is r cosine theta. Right? We know the explicit formula. We can explicitly take a partial, and likewise for y equals r sine theta. Okay. All right. Then we pointed out that, this formula that I have for the partial of z with respect to r, I can reasonably ask what happens when I take an r partial of that. Right? Now, taking an r partial means, among other things, that theta is to be treated as a constant. Right? Well, we're taking a partial with respect to r, and that means that cosine theta is a constant, and sine theta is a constant. Oh, and I forgot to hit the little button there. There we go. And cosine theta being a constant and sine theta being a constant, I factor those out like so. And I believe this is where we left off, and we found ourselves trying to figure out now how are we going to make sense out of, for example, this thing right here, partial of zx with respect to r. Is everybody with me so far? Look familiar from last time? Okay, so I want to warn you off of a misguided take on this, and that is to figure, all right, well, I've got z, and apparently I'm taking an x partial, and then I'm doing an r partial, so why don't I just view this as zxr? I'm going to put a question mark next to this. Can't I just view this as zxr? What's wrong with that? What's wrong with that is this assumes something unreasonable about what z is a function of. This makes it look like z is a function of a collection of variables including both x and r. In other words, that z is a function of these four variables. This doesn't make any sense because, for example, x is a function of r, right? So I couldn't even talk about what is, for example, what is the partial of z with respect to r? You can't have a partial of z with respect to r. That would require that I hold these other variables on constant, and they aren't. They're functions. Right, so that's a nonsensical. It's a nonsensical thing. Doesn't make any sense, and so please don't make the mistake of thinking that you can write it this way. That's not a reasonable thing to write. So what are we going to do then instead? And the big idea. This is really one of the big ideas of this example. Is that look, if z. Oh, I'm sorry. I wanted to be in highlighter mode. If z is a function of x and y, just think about what that means. Z is some expression that has a bunch of x's and y's in it. What do you suppose zx would be? Zx would be a different, slightly different, great big expression involving x's and y's. Zx would be a function of x and y. And so on my diagram, with z understood to be a function of x and y, I'm going to rewrite zx as being a function of x and y, because it is. And I'm going to include it correspondingly on my diagram. So that's how I'm going to interpret that zx right there. It's a effectively kind of a variable on my diagram. And then likewise, let's see here, color choices, zy. Also, a function of x and y, so represented correspondingly on my diagram. So notice I've added to my original diagram. I initially had just this, but now, because new stuff has showed up, I append my diagram to include the new stuff. Everybody with me? Okay. And now, making sense out of what we're looking at here. Again, we're still trying to make sense out of what is the partial of zx with respect to r. And no problem. Zx, here it is. It's right there on my diagram. You want to take the partial with respect to r? Okay, cool. There's r on the diagram. What are the intermediate variables? What are the various paths that get you from r to zx on this diagram? Well, there's two paths and therefore two terms in this expression for partial of zx with respect to r. How are we doing so far? Yeah, question.
Wait, so is that the product rule with the partial of r?
No, it's not a product rule. It's the chain rule. So zx is just a single thing. It's the partial of z with respect to x. Right? So it is whatever it is. The point is it's here on the diagram, and there are two paths that get you there by way of r that we're taking the partial with respect to.
So we have to include both paths.
Yeah, it's straight up the chain rule, right? It's the chain rule applied to our sort of carefully thought out and appended, updated diagram. Yeah.
How did you create that diagram?
Yeah, so the idea was, I started off, right? We were initially told z is a function of x and y, and that r and theta are polar coordinates. So I had that, right? And then I just made this interpretation that, look, if z is a function of x and y, so are its partial derivatives. And now let me say that differently. If the partial derivatives, let me clean this up. If these partial derivatives are functions of x and y, then this is where they go on the diagram. I just literally indicating that zx is a function of x and y, and zy is a function of x and y. Yeah. All right. Okay. Yeah, cool. Now, good news. Cosine theta comes along for the ride. Nothing happened there. It's still there. And now we can make an analogous argument for the partial of zy with respect to r. Again, let's label what's where. There's zy. Taking the partial with respect to r, which is there. Think about the various different paths. How do you get to zy from r? We have two paths and thus two terms in the chain rule that I use to rewrite this composition partial derivative. Everybody on board? So it's all kind of details from here on down, right? This is the big point. The big point is to realize that once you've written down zx and zy, you have to include them on the diagram. Include them right where they go, right where it makes sense. And then having kept your diagram sort of up to date and complete, then just follow the instructions. Just do what the chain rule says, right? Identifying, where is the thing you're taking the partial of, where is the thing you're taking its partial with respect to, and looking at intermediate variables to guide you on terms. Okay. All right. Now I claim it's all sort of downhill from here. I'll point out a couple of those bits. Partial of zx with respect to x really is just zxx. Z is directly a function of x. There's no chain rule involved there. There's no intermediate variables. So you got z, you take an x partial, you take another x partial. That's the x second partial. Likewise, here, and here. That's just rewrites. Notice that is just, again, polar coordinates. We know the formulas for x and y in terms of r and theta explicitly. So you just write those down. right? And then, of course, these constant factors over here come along for the ride as constants do. Okay. Then it's just a matter of kind of writing, multiplying terms together and collecting when everything lines up, and that gets you to your final answer, which is that right there. Okay. Now let's address the question of why we would ever care about such a thing. Why is it interesting to want to take second partials with respect to polar coordinates? And I have an example on the next page here. I'm going to talk about something called the Laplacian operator. And here it is, the Laplacian operator denoted by that symbol. Now, notice that looks an awful lot like the little triangle that we use to represent gradient. The difference is it's kind of flipped, right? This is what you might call right side up. The gradient, notation is sort of what you might call upside down. They're not interchangeable. They mean significantly different things. You've got to get it straight. So anyway, be careful with that. Make sure you use the right one in the right place. So the Laplacian is this formula right here. Let's see here. It's, here you go. It's the sum of the three rectangular second partials. It's extremely natural in this physical world we live in. Understanding waves, heat transfer, electric potential, stuff like that, all involves heavy use of this operator, the Laplacian. So, big deal. We need to understand how to solve equations that involve the Laplacian. And as written, it's very convenient for addressing functions that are written in rectangular coordinates because the partials are with respect to rectangular coordinates. But sometimes your function might be in spherical coordinates. And as it turns out, if you want to do the same thing, you still want to talk about the Laplacian, but you want to do it in spherical coordinates, it's this thing right here, this much uglier looking nightmare seeming thing, if you want to do it in spherical coordinates and get the same answer. So where on earth does this come from? Well, this is where we're going to make use of the stuff on the previous page. For example, keep in mind, if I have a function of position, that means f is a function of x, y, and z. And if I want to understand it in spherical coordinates, keep in mind, spherical coordinates means x, y, and z are functions of rho, phi, and theta. Right? Then I have myself a pretty analogous situation to what we had on the previous page. We have a composition where sort of the first part of the composition is just coordinate system conversion formulas. This is spherical instead of polar, but I mean it's highly analogous. Okay, so for example, I could then ask, what's that? Second partial with respect to theta. Well, here's f, here's theta, and just like we saw on the previous page, we have a chain rule partial to which we are then going to do another chain rule partial. So it's evaluating that's just this part. Just this one little part here, you'll notice is basically one of these problems here. Okay, and now the bad news is that it keeps going, right? You've got to take that result and you've got to divide by rho squared sine squared phi, and then you've got to take a phi partial, and then you've got to multiply that, and then you've got to take a phi partial of all of that, and blah, blah, blah. Now, I have on several occasions in the past said, suggested exercise, work this out for yourself. I want to emphasize I'm not suggesting that here. It's really hairy, right? It's more than I would want to impose on you. And in my past as a physics major, I did have to do that one time, and it's a lot. And so I'm not advising it, but if you wanted, if you're looking for a challenge, go ahead. But like I say, I'm not recommending it. But if you did, you would get that this simplifies to that in rectangular coordinates. So these compute the same thing because of arguments that we can make on the previous page, adapted to here. Okay, still with the who cares. How does this help me, right? And here's how. Let's suppose you want to understand gravitational potentials. By the way, gravitational potentials, they come from gravitational fields, right, which we all know are relevant to the world we live in, right? Electric fields and electric potentials, as it turns out, are really analogous. So the computation I'm going to show you applies to both gravitational potentials and electric potentials, aka voltage, right, for those engineers out there. And they have to satisfy what is called Laplace's equation, which says the Laplacian has to work out to be zero. Why that is a physics discussion. That's not our problem. But that is, how it turns out. So what the answer ends up being, the function that makes this work is this right here. Now you'll notice I have it written in rectangular coordinates, but I also have it written in spherical coordinates. So when you're looking at confirming that this actually works, which again, you kind of have to do if you want to understand why gravitational potential is what it is, you got to be able to plug it in, confirm that the Laplacian is zero. So option A would be to take your rectangular candidate function, apply the Laplacian written in rectangular coordinates, and kind of crank out this whole thing and confirm you actually get zero. And everybody should do this one once in their lives. I've done mine. Right, it's your turn. You don't have to do it now, but there is going to be a homework exercise coming up at some point where you will actually have to directly compute this thing. It's a little annoying, but it's not that bad. It's perfectly doable. It'll take you 20 minutes. I've had more fun in 20 minutes than this, but it's perfectly doable. And when you do it, you'll notice how the algebra works out in certain ways. It's actually kind of instructive, so I think it is a healthy exercise. Still kind of tedious, and nobody wants to do it more than once. Right? So that's your first option. Let's call that plan B. Here's your second option. Your second option is to take the spherical formula for our candidate function. Take the spherical Laplace. Oh, whoops, wrong color. I keep seeing the purple and thinking it's the red, and vice versa. Take our spherical Laplacian and crank this out. That's your second alternative. And that looks even worse. But it's not. That's the beauty of this example. This second option down here is downright easy. It's so easy, we're going to do it right here in class, and I'm not even going to have to write anything down. That's how easy this is. You really got to love it how this calculation works. It's a kind of a thing of beauty. So here we go, seeing that I'm, again, computing the left side of Laplace's equation. Here it is, left side. I need to crank this out. I better get zero. That's my answer. Here it comes. Take this one term at a time. Notice we have three terms here. Starting with the right term. Notice the first thing I need to do is take a theta partial of this function. Oh, hey, wait a second. A theta partial, there's no thetas in here. That's zero. And so multiplying it by something else still 0, and effectively what works out then is that in this example, this whole term disappears in a puff of smoke. Yeah? Everybody with me? I love it. Likewise, looking at this term, very first thing, phi partial of that function. Oh, there's no phis in there. Sweet. It's again 0. That disappears in a puff of smoke. We're like 2/3 of the way done. We still haven't done any actual effort. Yeah? All right. Beautifully. Proceeding. Now, we actually are going to have to do a slight little bit of effort here, but not much. You can take the row partial of this. Easy calculation. There is a factor of 1 over rho squared, which, when you multiply by this rho squared, right, we have rho squared times 1 over rho squared, makes this thing here a great big constant. And the row partial of a constant is 0, and we win. Game over. Everybody with me? So it's just kind of beautiful. Everything just kind of lines up, right? And ultimately, what makes this all come together is that while the familiar, let me use a better color here. While the familiar formula for this function in rectangular coordinates, I'm more comfortable with x, y, and z, but it is, there are 3 different variables involved here. They're involved in an ugly way, and that's what makes the calculation nasty. By contrast, this expression, 2 of the 3 variables don't even show up. And the one that does, we have a simple formula for how this expression relates to that one apparent variable rho. So, sure, it looks worse, right? We're less optimistic, looking at this, or a little scared going into it, but it just works out really great. So the big moral here is spherical Laplacians can be really awesome. They are awesome because I can write down the formula by applying second derivative chain rule. Totally analogous to how we did here. This is what makes it all work, ultimately. Yeah? Mm-hmm.
So can we just say in this case that if it doesn't have phi or theta, then you know that you only have to... Yeah. Or if it does have phi or theta, then you know it's not a candidate immediately.
Oh no! Sadly, that it's not quite that simple. If I had a different candidate here that wasn't this, and it had phis and thetas in it, then it just means I'd have to work out all 3 terms. There's still a possibility that they might cancel. Yeah. But the point is, this one has already worked, and so I, in some sense, already have an answer. Yeah. Yep.
What are the parentheses doing? Does that mean that you're taking the partial of what's in the parentheses and then the partial of the k over rho?
You're talking about these parentheses here?
Yeah.
Okay. So what this means is, first I'm going to do is I'm going to take a phi partial of that, whatever that is, right? Then subsequently I'm going to multiply by sine phi, right? And then altogether, this whole thing is what I'm going to take a phi partial of. Yeah. And then all of that I'm going to multiply by that. Yeah. Is everybody good? Yeah, question.
So in the question before, so just going back a little, when you're given z is some function of x and y, but you're not given the exact. So I know the final answer is zxx. If you were given that for efficiency, would you want to wait until the very end to compute and then plug in zxx?
What we've done here is we've let's see here. I have rewritten effectively a second partial in polar coordinates in terms of second partials in rectangular coordinates, right? So this basically, what we've done here allows me to turn a polar problem into a rectangular problem. So how you make use of that depends on the circumstance. Yeah, I mean, the point is if you know z directly as a function of x and y, then these three rectangular partials are super easy you just write them down, and then knowing this formula in advance, then, well, whatever these partials are, you multiply by these polar functions and you're done. Yeah. Does that make sense? Mm-hmm. Okay. Cool. All right. Okay, so moving along. So we're going to talk about partial derivatives again. We're going to work up to a new idea called directional derivatives. But for the moment, we're going to start off talking about partial derivatives. And, color mistake. Partial derivatives. Here's the various things we know about partial derivatives already. We know it's the slope of the graph. Right? We know it's a multiplicative factor. It's what you multiply by input change to get output change under certain circumstances. I'm going to say we know this formula. We haven't actually written this down before, but let me just kind of walk you through what this formula means, and I'm going to zoom in. Can I? What's going on here? There we go. Okay. This on the right says, suppose I'm starting at some point A, and then you'll notice this construction A plus T times a vector. This is a parametric line that says I'm going to start at the point A, and I'm moving in the direction of this vector, but that's in the direction of the xi axis. So this says I'm wherever I am, but I'm moving in the xi direction. And as I move only in the xi direction, notice all this says is I'm taking the derivative of f with respect to t as I move in that direction. That is one of our interpretations of partial derivatives. And again, I hadn't written it down in this form before, but this is a kind of a way of writing down that it says how fast does the function change as you move in that specific direction. And then here's another thing we know about partial derivatives. We know this formula. And again, I hadn't really quite written this down before, but this is easy to crank out. The gradient is made up of just a bunch of partial derivatives, and EI is made up of a bunch of zeros, except for a single one in a particular position, and that one multiplied by the appropriate coordinate of the gradient gives you that corresponding partial derivative. Okay, so what we've got here then is four things that are all equal to the partial derivative, and I'm going to write this a little bit differently. I'm going to write this as these are four things that are all equal to each other. Right, the slope of the graph, the multiplicative factor, the rate of change as you move in the certain direction, and this dot product formula with the gradient. All of these are equal to each other. So now here's the question I want to ask. Under what other circumstances are these four things all equal to each other? Rhetorical question. So now, in this case, they're all equal to each other because I'm moving in the direction given by a specific unit vector, right? The EI vector, the vector that points in the direction of my xi axis, right? I've got an axis system, and this is as I move in that direction. These four things are then equal to each other. So here's the observation, the pitch I want to make for y'all. The direction of that axis is kind of arbitrary, if you think about it. Coordinates, they are what they are because we choose a basis. Y'all remember back in Math219, linear algebra, change a basis, right? You can use this, for example, as a basis, but you don't have to. You could just as well use this as a basis, right? So I like to make the observation, coordinates are really kind of an illusion. Coordinates are something that we make up so that we can do certain kinds of algebra more easily. But functions usually in real life, in the real world, are not usually actually functions of coordinates. think about, for example, temperature in this room. Temperature in this room depends on location. Right? The temperature here, it may be a little higher than the temperature here. It doesn't depend on the coordinates. The temperature at this point, the temperature at that point, they are what they are, independent of whether I write the coordinates with respect to this basis or whether I write the coordinates with respect to that basis. Who cares? Right? So notice that all of these four things that I say are equal to each other for these unit vectors, because they're the special ones, right? They're the standard basis vectors. They're only standard basis vectors because I chose to do this. I could just as well choose to do this. Now that's a standard basis vector. Right? Any unit vector could be a standard basis vector if I just chose my coordinate system accordingly. So the pitch I want to claim is that these four things are not just equal to each other when you're looking at this unit vector. These four things are equal to each other for any unit vector. Take your pick. Doesn't matter. Any unit vector. So in particular, Now it does have to be a unit vector. Right? But assuming you have a unit vector, this thing and that thing and the slope of the graph and the multiplicative factor, these are all equal to each other. Now, a question does come up. Okay, what am I going to call these things? I can't really call these partial derivatives. This thing that all four of these things are equal to, the term partial derivative suggests that I have made a choice of a coordinate system and that I'm going to stick with that choice, and the term partial derivative is reserved for whatever directions I have chosen to be my axis directions. So partial derivative as a term has been used for something else. So we have to make up a new name, and it's no big deal. Here's the name. The name we're going to use to describe this is directional derivative. Very common term. When you hear the term directional derivative, what I would encourage is for you to think, all right, well, it's morally a partial derivative. In fact, with respect to a different coordinate system, it is literally a partial derivative. But whatever, we're using the coordinate system we are, so this is morally a partial derivative. It behaves just like a partial derivative, and we just have to use a different term for it. And likewise, a different notation. Here is the notation that we use. Capital D for either directional or derivative. Take your pick. Maybe both. Whatever. Doesn't matter. The little subscript here of V indicates what is the unit vector that defines what direction you're going. And then, of course, you have to say what function are you talking about a directional derivative of, and where are you computing this directional derivative. So that part of the notation, I think, is pretty familiar, pretty standard. So that's what a directional derivative is. It's morally a partial derivative. It has all the properties, effectively, of a partial derivative. So slope of the graph as you go in the direction of the unit vector that you're talking about, that V unit vector, slope of the graph. Computed by, take your pick, either one of these formulas. Most of the time, in practice, we're going to use this dot product formula because it's easier to compute with most of the time. Okay. Now, one specific detail I do want to talk about, let's talk about this particular interpretation here, that it's a multiplicative factor. It's what you multiply by input change to get output change. Let's see here. I'm going to represent that. On here, let's see, input change, either a distance that I go in the indicated direction, or a speed at which I am moving in the indicated direction. Take your pick. And it's the factor that I multiply by that to get the output change. And again, it could be either, the estimated linearly estimated change in the output or the rate of change of the output. Take your pick. And now looking at these two equations down here, what would be a reasonable notation for what I multiply by the orange to get the blue? Right? I mean, you kind of use whatever notation makes sense. And in both of these cases, this notation, DFDS, really makes a lot of sense just in terms of, again, the sort of the sloppy intuition we have for canceling differentials, which in this case is kind of okay, as it were. So be aware of this very common notation for directional derivative, DFDS, and be aware furthermore that directional derivatives allow us to compute this thing that you would write DFDS. And let's think about how to interpret it. DFDS says, let me clean up the picture here. DFDS says the rate of change of your function with respect to distance traveled. Not to be confused with rate of change of the function with respect to time. Right? Change per unit time is one thing. This is change per unit distance. Okay. Everybody on board? Everybody with me? Yeah.
So in this case, I'm assuming DSDT you said would be some kind of like a velocity, so a distance over time. So would DS just be like a displacement?
Yeah, okay. Yeah. The DS would say, I should use my colors consistently. DS says, now keeping in mind that we're going in the direction prescribed by our V vector, and again, I'm conflating my notation, my colors here. DS just says, literally how far, how far have I gone in that direction? Yeah. All right. Okay, let's do one. So, we've got a function we're keeping track of, and I can talk about the graph of that function. The question says, what is the slope of the graph at a certain point pointing in a certain direction? Okay, well, conveniently, slope of the graph is one of our primary interpretations, one of our primary interpretations of directional derivative. This is already established. I don't have to make a case for this. I was asked to compute the slope of the graph. Cool, I'm going to compute the directional derivative. Oh, and side note, we already know that slope of the graph is equal to these various other things. So I can compute the directional derivative that is my slope. I can compute that directional derivative with any one of these formulas, and I like this one because dot products are easy. And gradients are made up of partial derivatives, which are easy. So this is the life is good formula right here. All right. So let's do it. We want to compute the slope of the graph. Cool. Directional derivative for which I compute with that formula, dot product of the gradient. Some details to go through to follow, but is everybody with me so far? Big picture. Alrighty, no sweat. Let's see here. Our gradient, partials, you got to evaluate at the given point. There's your gradient. Now there is a tricky bit here. I do have to dot that with my unit vector. This is a subtlety that a lot of students mess up on. Notice it is required that the vector be a unit vector. It's got to be a unit vector if you want to make this interpretation, if you want your thing that you're computing to actually give you slope of the graph. Unit vector, very important. I was not given a unit vector. All right, I was given this thing here, which is not a unit vector, but I can find the unit vector pointing in that direction by just dividing it by its own magnitude. That again is old formula from chapter 1. right? So sometimes called normalizing, which is a word that gets used for too many things. But anyway, don't forget to normalize your direction vector. Everybody on board? Yeah.
Do you think you can show us how you evaluate the slope using the formula for t?
Well, that would just be harder work, but yeah, I mean, I could. I mean, let me outline it, right? So the outline would be, because the whole point is you're basically never going to do this, right? But the outline is, all right, this is a point that has coordinates. The direction vector is a vector that has coordinates, and so you can explicitly write down, all of this right here, you could explicitly write down as it's going to be like P plus TA, Q plus TB, something like that, right? This is your X, and this is your Y, and all of that gets plugged into your function, right? F is a function of X and Y. So take this formula for X and this formula for Y, and you plug them into your whatever the formula is for the F function, and you'd get a great big function of T, which you would then take the derivative of with respect to T. And then don't forget to plug in T equals 0 at the end. So yeah, it's much more sort of tedious to do it that way. I suppose you could if you want, but in practice, vast majority of the time, there's no call to do it. Is that satisfying? Okay, cool. All right. Oh, whoops. I gotta delete all that. There we go. Okay. Yeah, we've got our unit vector. Whoops. Back to highlighter mode. Here we go. Unit vector, and then you dot it up, and there's your answer. Is that cool? All right. So the idea of a directional derivative saved us a bunch of trouble there. I don't have to kind of reinvent the wheel and figure out how to compute a slope in the direction of some vector and, going off at some angle. I just take advantage of the fact that slopes of graphs are directional derivatives, and that directional derivatives are computed by easy formulas. Okay. All right, here's before I go on to the next example, there is a little annoying terminology thing that I want to make sure everybody gets the heads up on. Notice it says in the direction of the vector 3, 4. It specifically says the vector 3, 4. So 3, 4 is a vector. It's not a point. And now, even if I hadn't said vector, even if I had just said, in the direction of 3, 4, how would we make sense out of this direction of 3, 4? Is 3, 4 to be understood to be a point or a vector? Well, it says direction, and points don't have directions, right? So even without the explicit indication that this should be interpreted as a vector, the mere fact that I'm talking about a direction, using 3, 4 to represent a direction, means that you, again, still have to interpret it as a vector. Now, students will sometimes misunderstand this and will conflate what I've got here and think of it as toward the point 3, 4. And that's just absolutely not what got said, right? And it's not how to make sense out of this question. So here's what such a student will then incorrectly do. The student will say, okay, we're at the point 3, 1. Fine, here's 3, 1. And when they should think in the direction 3, 4, they instead incorrectly move toward the point 3, 4, which would be here. And so the misinterpretation of the question has the student going that way, which is wrong, instead of that way, which is right. Everybody see the problem there? All right, so heads up, right? Make sure to interpret the question correctly. Again, that's part of the question, is to make sure to interpret it the way that you're supposed to interpret it. Okay, and if you're unclear about any of this, I want to give you my usual sort of perpetual reminder. Come to office hours. We'll talk about it. I'll be very happy to go on at length about this distinction and stuff like that. Okay. All right, here is another example. I've got some scenario here about temperature. I want to keep track of temperature given by an explicit function. And I'm at a certain point, and then the question says, how fast is the temperature changing with respect to distance? What's the rate of change with respect to distance? And again, reminder, that is one of our interpretations of directional derivative. Right, question asks for DFDS. Cool, that's what directional derivatives do. And by the way, also cool, again, we could use this handy formula right here, this dot with the gradient vector. Right, so that's what we're going to do in this example. Notice dTdS computed with directional derivative. Directional derivatives computed with that usual dot product. Right? And again, we find ourselves with just kind of a plug and chug sort of a situation. In particular, the gradient. You have to, take the appropriate partials, which admittedly a little annoying. That there's, chain rule, etc. But you just take the various partials, plug in the given point. There's your gradient. Oh, I'm sorry. Went too far. There's your gradient. Keep in mind further, direction of 2, 4, 3. So again, that has to be a unit vector. Right? So you've got to take your non-normalized vector and divide it by its own magnitude. Make sure you get a unit vector. And then again, dot product, arithmetic, answer. Everybody happy? All right. Here is an unfortunate cultural point. There is not uniform agreement in STEM communities, I'll say, what the term directional derivative means. Different people interpret the term directional derivative in different ways. Now, I want to emphasize, in this class, we've already got an established choice here. The term directional derivative, right? This notation means this formula, which you can compute with that formula, which you can interpret as slope as the graph, which you can view as a multiplicative factor, which you can interpret as DFDS. That's what directional derivative means in this class. And I'm going with this choice, this definition, because our book does. And, I feel like we have to stick with the book's conventions on that kind of thing, right? Otherwise, it'd be massively confusing, and that just wouldn't be appropriate, So that's what directional derivative means in Math219. Now, that said, outside of Math219, different people learned about directional derivatives in different contexts, in different books, and a lot of people very reasonably don't like to include this requirement about it being a unit vector, right? The thing is, you come back to this list of properties, and even without the unit vector requirement, let's see here, I guess I better erase all of this. Even without the unit vector requirement, this is still equal to that, which is still a useful thing because it tells you how fast the function is changing as you move with a certain velocity. Still useful. Still an important concept. Very convenient to have a term to use to describe that important concept. And so they use the same notation, unfortunately, right? Now the cost is when you abandon this idea of it being a unit vector, you can no longer interpret this thing as being a slope of a graph, or as being a multiplicative factor, or as being a DFDS. That you lose. right? But it's still the case that this easy formula computes this important quantity. So it's still an important idea. Now, what do we do about this? And I have two answers to this question. And that is, in Math219, the answer is really simple. We're going with this definition as previously written. We are going with that it does have to be a unit vector, and it is a slope, and it is a factor, and it is df/ds. That's what it is in Math219, and I don't want there to be any ambiguity about that. The second thing that I'm going to point out is what I can't control is that you do have to be heads up outside of this course. Again, there are plenty of people walking around that outside of the context of Math219 would rather not be burdened by this inconvenience of having to restrict their attention to unit vectors. Plenty of mathematicians, and I'll be totally honest, I'm one of them. Right? I actually, outside of this course, I would prefer not to have to deal with this restriction. So, your job outside of Math219 is to always be heads up. And if you hear someone say the term directional derivative, you have to ask yourself, wait a minute, what kind of person am I talking to here? Is this a unit vector kind of person, or is this one of the non-unit vector kind of people? And just be aware, it could be either. And so clarify, right? And make sure that you know what it is that you're dealing with. Let's see, I don't seem to have a. Let me look at my time situation here. Oh, I've got 3.5 minutes. Okay. No, I'm sorry. It's 2:30, not 2:35. I'm out of time. Okay, drawing the line right here. See y'all on Friday. Don't forget midterm exam on Friday. See you then.